All right. So today we're going to talk about GPUs, which stands for graphical processing units. But before we get onto that, I just want to have like a brief aside on how computers represent numbers, because I've realized that there's some confusion, and I just wanted to clarify it, just like how everything works. So the way we're used to representing numbers is in decimal, right? So if I wanted to write the number in basically, if say you want to write 123, well, 10 to the 0 is 1. So 3 is 3 times 10 to the 0. And then 20 is 2. So if we're trying to write 123, right? Then the 2 is, so the 20 is 2 times 10 to the 1, and 100 is 1 times 10 to the 2, right? And there's 0 times 10 to the 3. And that's how you write 123, right? And you can see each place is, a power. You start from power 10 to the power 0, and each place is an increasing power, right? You've all probably seen this before. You have also probably seen how you can do the same thing in binary. So if you want to write, for example, 12, well, let's see. So 12 is, what's the largest, the first thing you want to ask yourself is, what is the largest, when you're converting things like this, what's the largest power of 2 that I can fit in 12? And the answer is the largest power of 2 that you can fit in 12, right, is 8, because the next power of 2 after 8 is 16, which is bigger than 12. So 12 is an 8, and 12 is an 8, has an 8 in it. And if you subtract 8 from 12, you get 4. That's another power of 2. So then you're done, right? And now you just put in the 8th place, which is 2 to the 3, you put a 1. And in the 4th place, which is 2 squared, you put a 1. And then everywhere else is zeros, right? And this is how you represent numbers that don't have a sign. So does anyone have any questions here? Does this make sense to everyone? If it doesn't make sense, put a no. I don't think it'll show up on the recording. If you have a question, or drop a question in the chat. Okay, I'm going to assume everyone understands this. You've probably seen it before. So this is how you represent how computers typically represent numbers that don't have a sign. So yes. Christian asks, is there only one unique combination that gives 12? Yes, there's only one unique combination that gives 12, because you can only put a 0 or a 1 in each slot, right? So this is how you represent unsigned numbers. If you want, so now you want to be able to represent numbers that have signs. The obvious way to do it is you have some bits, right? So if we were doing 12 again, we said we want to do negative 12. Obvious way to do it is to just do this. You have the bits that represent the magnitude of the number, and then you have an extra bit. And if that bit's 0, then it's positive, and if the bit's 1, then it's negative. And some early computers did things this way. But if you think about it for a little bit, you'll notice that there's an obvious problem here, which is that now you have 2 zeros, because this is 0, right? This is negative 0, and this is positive 0. And I don't want to get super philosophical here, but I think most of us are pretty uncomfortable with the concept of a negative 0 and a positive 0. That's not necessarily something we want to be dealing with. The better way to do it, and better for actually a lot of reasons, although it seems non-obvious to begin with is to use a format called 2's complement. And 2's complement is basically, if you want to get a negative number from a number, right? So say you have number 12. To get that negative number, we're going to represent negative numbers as the inversion of all of these bits plus 1. So we have 12 here, and to invert it, to get negative 1, we invert all the bits and we add 1. Now this doesn't seem obviously better. But there's a, if you construct, so, okay, so say we have a 4-bit number, right? 4 bits. So say we have 0. What is -1? Well, one way of expressing -1 is to say -1 is 0 minus 1. And so how are we, so getting, so this is the smallest number we can represent with 4 binary digits, right? Now, if we subtract 1, this will wrap around to what in our unsigned format would be the highest number. So if we just let it wrap around to all 1s, right? We have -1, right? And in our unsigned number, we would call this 1 plus 2 is 3 plus 4 is, this would be 15 in our unsigned number. Now we're calling this -1. So we have the range, and you can still easily check what the sign is because the sign is going to be the last bit. So now we can represent numbers with this 4-bit number. We can represent 0 through 7 and -1 through -8, I think, just from memory. And so you get a bit this little mismatch here where you have one extra negative number. But for the most part, this works pretty well. And it actually turns out that the circuitry to add and subtract numbers that are represented in 2's complement, like positive and negative numbers, is exactly the same as the circuitry required to add and subtract sign numbers, because it does that wrapping thing. So this ends up being a big help for when you're designing computers, because basically whether a number is negative or positive is just dependent on how you decide to interpret it. And for a lot of operations, what you're actually doing is exactly the same, right? So we're basically just shifting, or actually it's not a shift. Okay, so this is how you represent sign numbers. I don't want to spend, does anyone have any questions about this? It's a bit weird, but it works really well. Okay, I'm going to move on to the next section, which is how we represent floating point numbers. So numbers like, 2.157, right? Numbers that have decimal digits. And the way we do this is actually pretty simple. So this is an example of a floating point number. Here we have, so this is a 16-bit floating point number. And we have 1 bit that represents the sign, right? So we call this bit S. We'll call this number E. And we'll call this number M, right? So we'll have a bit that represents the sign, 5 bits to represent the exponent, and this can be positive or negative. And then M, and then M is the magnitude, right? And basically there's a binary, this magnitude is in binary point. So there's like, so if you've ever done, there's a decimal point, right? And everything past here is like 10 to the -1, 10 to the -2, 10 to the -3, right? Everything past here is, 2 to the -1, 2 to the -2, 2 to the -3, right? So this lets you represent, so, if we decide we're going to pick our binary point to be here, now we can represent numbers between 0 and, so if just this magnitude can represent numbers between 0 and 1.111111, which is like, 1.99 something, right? So the way we represent numbers overall is we take our magnitude. So if we interpret this in binary point, we take our magnitude, multiply it by 2 to the exponent, and we multiply it by -1, right? So this is how you get if you have, the value of each of these fields, which are all packed together, to get the value of that number, you multiply the magnitude by 2 to the exponent times -1 to the sign, right? So basically, if this is a 1, it's negative. If it's a 0, it's positive. And there are a lot of kind of weird things about this format that are around for legacy reasons. For example, the binary point is actually here, and there is always assumed to be a 1 here, so it's not explicitly stored. But for the most part, you can just think of it how we have written here. The other thing is the exponent. Oh, the exponent is actually not in 2's complement. It's in a funny signed number format. Okay. Does this kind of make sense? This is probably kind of weird, and I want to see if anyone has questions before we move on, because this is the last time I'm going to talk about floating point numbers unless people have questions. Basically, floating point numbers are how you represent like things with decimal places, and if someone says float 32, if you see that anywhere, it's in a couple places in the code for the next homework. That means a float that is represented by 32 total bits. So like the sign bits plus the exponent bits plus the magnitude bits. There are 32 of them. And that's kind of like the standard, like low precision. And then a lot of science uses 64-bit floats, which have much more precision. Okay, if there's no questions, I'm going to move on to something completely different. Okay. Nominally, this lecture is supposed to be about GPUs. So what is a GPU? So early on in the history of computers, people realized that people wanted to talk to their computers through more than just a keyboard and then a printer that printed out text, right? And so to do this, they figured out how to attach computers to TV screens. It turns out it takes a lot of processing power to every 60th of a second draw thousands of pixels, even for the lowest resolution screens that were available in like the 80s. It takes a lot of processing power to figure out how to draw like even just text in a way that didn't just use up all of the processing power of your computer if you're trying to do it from the CPU. And early solutions were just text only. There would be a special chip that was basically a special chip designed just to render text to the screen. And that worked for a while when people were happy with just having computers that just had text come out on the screen, right? Like, your Apple IIs or whatever. We're all too young to have been in this era, but it probably existed. Now, at some point, to make computers more user-friendly, we wanted to start adding graphics with, crazy things like mouses and then like context menus, all that. Turns out that's way harder than even drawing text. So people started building special chips called graphical processing units that would be attached to the computer, and all of the processing, all the management of the display, and all of the processing of a lot of things would happen in the graphical processing unit. And your computer would just send a command to the GPU saying, draw a square at this location. And that's all the interaction, all the computational power that would be required on your CPU to draw that square. And then the GPU would have a bunch of special hardware to do this in a way that didn't eat up a lot of power, right? Like custom designed hardware. And people kind of started just, iterating on that custom designed hardware. So bringing us to the modern day, what does a GPU look like? A GPU is a computer, right? That's attached to your computer. There's actually a lot of computers attached to your computer. Your computer is actually like about 100 computers put together in one little case. It's quite amazing. Over a relatively low bandwidth. And when I say low bandwidth, I mean like, 100 times faster than the internet connection you're watching this on right now. But relative to other things in the system, relatively low bandwidth connection, right? That they can use to share things like pictures that the CPU wants drawn to the screen, commands to, draw a cursor at this location, right? low bandwidth connection. And the GPU will be a little box with some memory on it to store, textures and 3D models and stuff that want to be drawn to the screen. And it has a very high bandwidth connection to some memory. And your CPU will have its own memory that is really quick. Like it can access it. Like when it requests something, it'll be available really quick, fast, but doesn't necessarily have a whole lot of bandwidth available. So like it's like you're shipping something on a motorbike. Like the motorbike will get to the place fast, but you can't exactly ship a container on a motorbike, right? Whereas this is more like a container ship, this connection here. And then this is like a Dutch person on a bicycle compared to the other two. Like, not bad, but, it's not as fast as either of these links, right? And your GPU will be the thing that's actually connected to your monitor. So it can handle all the rendering, and if the GPU draws something, it doesn't have to send that back to the CPU in order for it to go to the monitor, right? So this is, we're in the year 2000. This is what your computer looks like. And you have this GPU. And you might ask, okay, what does this GPU look like inside? Is there anything I can use? And if you're in 2000, your GPU looks a lot like this. So in memory somewhere will be a bunch of data, like some point cloud that describes, a 3D model, or like how, like, or even just like, a 2D model, like of a thing you might want to display on the screen, right? And that mesh cloud, like that large memory bank of triangles, will get read by a dedicated piece of hardware that reads triangles, reads their position, and figures out which triangles are in front of which other triangles, right? So this will output, which, for every point on your screen, which triangle is in the front, which triangle is closest to the screen, right? And then that will send out those triangles to a dedicated engine that paints images on those triangles. So this engine says, okay, I know on this part of the screen, this triangle is being displayed, and I know this triangle is supposed to be this color. And it will go out to it'll go out to some memory that has some pictures in it. And it'll bring in those pictures, and it will paint those those triangles with those colors, right? And then it will go to some dedicated color processing engine, and that processing engine can do things like, apply tints to the whole image, or convert from one color format to another. Say if your texture is like a PNG and your display doesn't support that. It's not actually PNGs, but like, if this is like, a grayscale image and your TV screen wants a full color image, right? There's a dedicated engine to convert between those things. And if you're in 2000, this works really well. All your applications are basically like very simple 3D graphics or very simple 2D graphics, and you're not doing a whole lot. And for the most part, you can just get away with this, right? But a problem comes in. What if, for example, you start to run an application that has a lot of triangles in it, but very simple textures and doesn't do much color processing? Now, all of your work is happening in here, and these blocks are mostly idle. And if you're trying to build a GPU that is useful for a lot of applications, all of the ratios of processing power that you put into each of these things are literally baked in by 1,000-degree ovens when you make the device. You can't change them. So a company called NVIDIA, which you may have heard of, a very small company at the time, had this really bright idea. What if, instead of having a dedicated engine for every single part of the graphics pipeline, what if we designed something that was more general, but could be used to accelerate each stage? So kind of a processor that is pretty good at all these tasks and is optimized to be able to do all these tasks really well, but is general enough to run any of them. And NVIDIA came up with a common processor that is good at all these things. So they want a common processor, right? And then you have code that processes meshes of triangles, code that processes textures, and code that processes colors. Now, around this time, people were trying to build supercomputers in, like far-flung regions of Australia, right? And they didn't have a lot of power. And they, oh, sorry, someone asked a question I missed. They didn't have so just back to the story. They didn't have a lot of power in Australia, and they wanted to do a lot of Fourier transforms because they were doing radio astronomy. Just keep that in your mind for a second. So Suprav asked, why is the connection between the CPU and the GPU low bandwidth and high latency? I thought that there's a lot of data sent back and forth to do the visuals and rendering. Yes, so Suprav is right. In absolute terms, the bandwidth here is 32 gigabits per second, right? That's really fast. Your internet's nowhere near that fast, and the latency here is maybe 100 nanoseconds. That's also pretty fast, right? But the thing is, the latency here is like 25 nanoseconds, and the bandwidth is 60 gigabits per second. And the latency here, the bandwidth here is 120 gigabits per second, right? And the latency is it's like 50 nanoseconds, right? Obviously these numbers get smaller every year, but this is like these ratios are generally pretty good guesses. And the reason this link is like that is because this link is just physically longer than these two links, because just because of the way that computers are laid out. So it has to have more error correction, and it just physically takes longer for signals to travel, and for every transfer you have to talk back and forth. So this is a pretty high bandwidth link, but when you actually do rendering, the majority of the work that goes into optimizing like a game, or as you'll see, a program, is actually goes into trying to keep as much data as possible in the GPU's memory and trying to minimize the traffic across this link. So you're only using it for what you need. And that is where most of your performance boost is going to come from. Like if you have a program on here, the place you're going to want to start, first place you want to take a look at when you start optimizing is, how can I reduce the traffic between the CPU and the GPU? Okay, I hope that answers Suprav's question. Does that kind of make sense? Okay, so back to Australia. So you're in Australia, you're building this big radio telescope, you don't have a lot of power, and you're trying to do something, you're trying to build a supercomputer to process radio data before shipping it out to a place that has more power, right? Because you're in the middle of the desert. So they took a look at this GPU architecture. So what did this common processor that NVIDIA came up with actually look like? Okay, so this is a common processor. NVIDIA calls it a stream module. Every different GPU vendor has a different name for this type of thing, and they all work basically the same way, but with loads of tiny different details, right? So the common processor basically has a very simple CPU, right? Thousands of shared registers, and then a lot of floating point units. So things that can say, add two floating point numbers, or multiply them, or divide one floating point number by another. Each of these floating point units can do one of those operations, right? And these registers, the ones like we handled in homework 3, are shared between all of these floating point units, right? And then there are a couple load store units which can copy floating point numbers between memory and these registers, right? And basically, this simple processor at the top takes in an instruction stream. So check if triangle 1z position is less than try 2.z. And so it'll get this instruction like, take this triangle memory, check if the z position of this triangle is less than the z position of this other triangle. So for example, just see which triangle is in, just kind of sort the triangles in your graphics pipeline to try to see which one is actually the one that is visible to the screen, right? So it'll get this instruction, and it'll see I have all these floating point units. Are any of them not currently doing anything? Oh, sorry. And if it sees that one of the floating point units is not currently doing anything, it'll schedule that instruction on the floating point unit, and say it'll schedule it on this one, and it'll check if it'll have this floating point unit run that instruction. It'll assign registers for triangle 1.z and triangle 2.z. It'll assign registers for these variables inside many shared registers, right? And then if it gets another instruction, which is like, take the dot product of these two arrays, right? It'll, assign the x part of the dot product to this one. It'll check if this one's free. It'll see it's still computing, this comparison. So it'll assign the y part of the dot product to this, and it'll assign the z product of the dot product to this. And if you're trying to do a lot of math on arrays very quickly, and you're a scientist, and you don't have a lot of power, and these devices are optimized for power because they're supposed to go in your computer and not make much noise, this looks like a really good model for you, because when you're writing scientific code, you're basically, a lot of times you're doing, you're taking the Fourier transform of terabytes of data, or you're doing a very simple thing on a lot of data. That's kind of a pattern that you've probably seen that comes up a lot. That doesn't work very well on a CPU because you've got all this extra cruft that makes running user programs fast. So running, like loading a web page fast. The requirements to do that are very different than the requirements to do a matrix multiplication. And most processors are optimized to load web pages fast because that's what users do. But it turns out that the kind of workload that you're trying to do is the same workload that in the 90s people realized that they should offload to a secondary processor because it was taking up too much time on the CPU. So they realized that they can use these same floating point units, which are standard, and do matrix multiplications or do dot products, right? Or do Fourier transforms. And so they started working on this. At the time, NVIDIA was, they made graphics cards, but they made graphics cards for gamers, or graphics cards for like people doing computer-aided design, like designing 3D models, right? If you look at like the boxes that the GPUs came in from the time, they're like pretty cringy. Now you think of NVIDIA as this like big giant computing company, and their big innovation that they did before anyone else really is they wrote a library called CUDA, which is still around today, which lets you write code in a language that's a lot like C and have it run on the GPU. And it does it really well. Yeah, Aditya said, yeah, there's no relation to me. It's called CUDA for completely different, like it's an acronym for something. It's a really amusing coincidence to me because they named their part of their like GPU architecture CUDA, and I might want to design an accelerator architecture at some point, but because NVIDIA has trademarked CUDA, I can never name it after myself. It's really sad.
You only have 4 other names to use.
I only have 4 other names to use. That Aditya is right. This is unrelated to me or anyone who I am related to, just to be very clear. Okay, so they wrote this nice library that lets you actually use this. And people started using this all over the world to do scientific computing. Currently, if you look at the top 10 supercomputer lists, I think all but 2 of them use NVIDIA GPUs. And the only reason, or like maybe some of them use AMD GPUs. And the only reason those 2 supercomputers that don't use GPUs is basically because all of the companies that make GPUs are US based, and those supercomputers are not US based, and they want to use them for simulating nuclear weapons, and they don't feel comfortable, like, China doesn't feel comfortable relying on the US computing supply chain to simulate nuclear weapons. And that's basically the only reason those supercomputers don't use GPUs, because GPUs work really well for a lot of supercomputing workloads. And also recently, not really recently, like 2012, when people realized that they could teach machines things with fancy processes called machine learning that don't make any sense, which are really just piles of linear algebra that people pulled out of their asses. GPUs are really good at that too. I don't believe in machine learning. I've never seen a machine learn.
Yeah, I don't either, but that's a topic for another day, another lecture. Machine learning is basically just very smart stats.
Yeah. Okay. So you built this little common processor. Now you want to put it together on a chip. So this is what that generally looks like, right? So they'll, cram as many of these common processors, or as like NVIDIA likes to call them, stream modules, onto a chip as they can. And these days, the low-end GPUs will have like 2 dozen. The high-end GPUs will have hundreds, right? They'll cram a bunch of them onto the chip. They'll throw a big piece of cache so that they can generally access memory pretty fast. There'll be, some random processor that pulls all the strings and makes everything work, like a little management engine. And there'll be a memory interface with a really fast bus to, like, fast as in can transfer a lot of data, but not necessarily on short notice to the memory. And then there'll be a little bitty, in comparison, PCIe link to the host computer. And then if it's a GPU that's made for using at like home, which increasingly less of them are, they don't actually do any graphics processing, even though they're called graphics processing units. They'll add a little display interface to, in like talk HDMI to a TV, or talk DVI, or whatever the latest standard is. And these will all talk to each other. And okay, so you have all this work. So you have all these processors that can do work, right? What does your execution model look like? Like, how do you write code for this massively parallel device that doesn't look a lot like a CPU, doesn't look a lot like most of the things you're probably used to, right? Because it's this weird, it's got like a weird amount of parallelism in it. So this is kind of a NVIDIA specific thing, but we're going to talk about the execution model here. The execution model I'm talking about is I am explicitly using a lot of the NVIDIA words for things. The execution model, if you're trying to write code for like an AMD GPU, for example, they will just, for the most part, just have different words for these things. Okay. Just to get that out of the way. So the basic unit of computation in these in your programming model is what's called a thread. And a thread is basically a little function, and it'll take some number of arguments, and it will return a result. And typically the way you want to organize your code is it's a thread in, actually, sorry, I should mention, it's a thread in much the same sense as the threads we talked about in the multi-threading section of the course are. Okay. So you have these threads, right? These are basically little functions, and they might take 2 inputs, like here and here, and this thread will take A and B, and it'll multiply them together, and it'll store them here. And then this thread here will take B and C and multiply them together and store them here, and so on and so forth, right? Each of these threads has its own little element in the output, and basically it only cares about its own little element in the output, and it does whatever it needs to compute the it's part of the output result, right? These threads are further grouped into thread blocks. And you might ask, okay, why group these threads into blocks of threads? Why not just have a flat array of, we have thread 0 through thread 100? So these thread blocks are kind of the execution model analogy of the common processor. And I just threw a lot of buzzwords in there. But basically, every thread block will, you might say, okay, I want to make 100 thread blocks, right? And you'll tell that to the management engine. And the management engine will have, okay, I have this queue of, thread blocks that I've been told to execute, blocks of threads. And it will say, okay, I'm going to assign one of these blocks of threads to this common processor. I'm going to assign this common processor, and then I have another common thread block that's in the input, and it's going to be assigned here, right? And I'm just going to, assign thread blocks until I don't have any more common processors that are free. And I'm just going to if the CPU tells me to execute more stuff, I'm just going to wait until one of these thread blocks is done executing, right? And this is basically the same thing that we described here with how instructions get allocated to the FPUs, but just one level up, right? So basically, thread blocks get mapped one-to-one onto common processors. And in like the time space, over time, more than one thread block might run on a single common processor stream module, right? And then those compute their results, right? And then you want enough threads in here so that you can keep all of the little computational units in the common processor occupied at any given time, right? So you want to put pressure on these FPUs with your threads. You want to pick a number of threads per block such that your FPUs are all always active. They're all always doing something. Okay, so that's your execution model. The code for this is basically, so what does your thread look like, right? It has an input array and an output array. It'll query what block number it's in. It'll query what thread it is in that block, and it will query the number of threads per block, right? And it will just compute an index, right? A unique index for this thread, right? That's the thread number in the block plus the number of threads per block times the block number it's in, right? And this index is unique, right? And then it'll basically say, okay, making sure that, because like if your block size is 4 and your array size is not a multiple of 4, like it's a multiple of 3, for example, then you'll have a couple extra dangling threads that are logically mapped to elements of the array that don't actually exist. So you'll check that your thread will check to make sure that the index that it's computed is less than the input length, right? And then for the code that we demonstrated earlier, you take two elements, you multiply them together, you compute, you extract A from the input and you extract B from the input, right? And then you set the appropriate element in the output, right? Okay. So now we're going to use the speedy version of the NumPy part of this lecture. Okay, so how do you actually do this in practice? Well, like all good things in Python, you use Numba and NumPy to make your code actually run fast. So from Numba has a module called CUDA, and CUDA is the interface to NVIDIA GPUs. And you'll use CUDA to write code for the GPU. So just running these cells, right? We're going to create a data set of a bunch of random numbers, right? We have this little NumPy function that computes the first couple terms of the Taylor series for e to the x, right? And we're going to see how long this NumPy function takes. So the NumPy function takes 48.6 milliseconds to operate on 10 million elements. So compute 10 million approximations of e to the x, right? So trying the So first, we're going to just use the methods we used in the last lecture, right? So we're going to have Numba automatically parallelize this code and run it on the CPU. So parallel on the CPU. And you can see that's quite a bit faster. We get about 5 or 6x speed up, which makes sense because we've got about 4 cores on here and with 8 logical threads, right? So fortunately, Numba has a way to automatically, so this is all on the CPU, everything we've done so far, these two things. Now, Numba also has a way for, like in the vectorized decorator, there's a target parallel for the CPU. There's also a target equals CUDA. So we're going to have the, we're going to have Numba automatically parallelize this application, right? So it's basically the same thing as we have here. You'll notice I explicitly said I want these constants to be 32-bit floats because the GPU I'm running on this on has a lot of really good support for 32-bit floats, really bad support for 64-bit floats, which is the default. So I'm telling it that these should be 32 bits. And then I'm having it run this CUDA vectorized function on our input data set. And you're going to hope that this is faster. Turns out it's actually not faster than our parallel implementation. It's a little bit faster than our NumPy implementation. That's pretty sad, right? We went through, we talked a whole lot about a bunch of different stuff. And in the end, this version that was automatically parallelized with Numba ended up being slower than the version that just runs on the CPU. And there's actually a reason for that. So dataset right here, dataset is declared on the CPU. Dataset lives in the CPU's memory. So if we go back to our architecture diagram here, dataset lives here. In order for the GPU to compute everything and return a result, dataset has to be copied into the GPU's memory, and then only then can we start executing our code on the GPU. So if we explicitly copy using numba.cuda.toDevice, which is a function that explicitly says, take this array, copy it into the GPU's memory, and return an object that references the array that is now in the GPU's memory. And we use our automatically generated CUDA function, we do a lot better. 3.73 milliseconds. That's about twice as fast as it was on the CPU. And if you keep increasing your problem size, and I didn't do it for this because I want, to be able to see the results in a couple seconds, you'll actually find that the GPU does quite a bit better than the CPU as the problem size increases, right? Because it can take advantage of more common processors, right? So let's look at the type returned from this from an execution of our CUDA function. So you might expect it to return a NumPy array. It actually returns this weird numba.cuda.cuda-driver.device-array.device-nd array. So this is an array on the device. And if you check, this array is a newly allocated array. When we called this vectorized function made a new array for us in the call to this, right? So this is, if I check if this is equal to the GPU data set, right, it should have the same size, but the array itself is actually not the same. The size is the same, right? But it's a different separate array. So the GPU had to go and make a new array of a new size, right? So if you write your applications in a good way, a lot of times you only need the output for a little bit. And if you keep that output array around, you can just overwrite it later, and you don't have to allocate new memory for it every time. So to do this, we're not going to be able to use the automatic vectorization here. We're going to have to explicitly write our own CUDA kernel and invoke it. So the way we do this is we write basically like the example that we discussed on the last slide, right? We use we decorate it with CUDA.jit, unlike ngit. So it's a lot like ngit, but it's for the GPU, right? And it takes X an array and it returns R. It returns the result in an array R, right? Now, if you remember from the example, we had a lot of stuff that we did to compute the index. This is a very common operation. So Numba has a function that basically just returns your position in the array. Like it just does all that math for you. You know, the threads per block times block ID plus thread ID, right? The CUDA.grid1 just returns, you know, the position of this thread in a one-dimensional array of threads, right? Then we just check to make sure pos, the position is less than the size of the array. And we do our Taylor expansion, again, using, you know, telling it that I want these constants. I'm basically here, I'm hinting to Numba that these constants only need to be 32-bit floats. That's what I'm doing here with the mb.float32 of 2, right? And I'm setting the result at that position equal to the Taylor series for e to the x of the value of x at the position, right? So if we explicitly allocate our array beforehand, so we've done this. We've created this little kernel. Sorry, how do we run this kernel? So we're going to make a little wrapper function, explicit CUDA wrap. Oh, wait, shit. Which takes you know, the x position and the return result. And it also has an optional argument block size, which sets the number of threads per block, right? So from that and the size of the array, it computes the number of blocks that we need to fit enough threads to operate on every element, but no more, right? So that's what this is. So we take the size of the array, and then we add block size, we subtract 1, and then we do an integer division by block size. So we get an integer number of blocks, right? And then we kind of use this weird syntax where it's a very weird syntax where it seems like you're indexing into the function, but basically this invokes e explicit CUDA, so our little kernel we wrote up here, with blocks, and a block size of whatever is set up here, right? So that many threads per block. And it invokes it with the arguments x and r. And if we run this new thing, and we time, without allocating, we time how long it takes to actually run the computation part of the computation. So without allocating the return array, we can see that it actually goes a lot faster. Now it looks like it's going a lot slower, but that's just because it's going so fast that that IPython has to run more runs to lower the standard deviation. And if we run this, and I really hope it'll finish, I really, really hope it'll finish and the kernel didn't just crash. The computer is making noise behind me, so I think this is working.
Okay, well, while we're waiting for that, I might as well mention homework 3's out, and it's on the assignments channel in Discord. And we'll shortly be distributing instructions for how you can access this server that Alan's using right now to do the homework.
The long story short for that is if you go to jupyter.ldcd.net, it'll ask for you for a username and a password. Your username is going to be your first name or the preferred name you put in when you filled out the survey for this class, and the password, right? So you probably don't have a password yet. Password is going to be basically whatever you put in this box the first time you sign in will become your password. It's a little bit counterintuitive, but that's just how it works. I didn't write the software. So you do that, remember that password, make sure you remember that password, and it'll give you like a data hub style thing where you can run notebooks. All right, so this finished. So without explicitly allocating memory for the result, it takes 891 microseconds to do the actual computation part. That is about 4 times faster than when we allocate a result. So you can see, if you can phrase your problem in a way where you don't necessarily, like, you can safely overwrite data, like you can safely reuse memory without allocating new memory, you can get pretty big speed improvements. Now, of course, to be fair, our parallel version for the CPU that we ran up here is, it does allocate memory. So I wrote a little version down here that does not allocate memory, and it turns out it's a little bit slower because Numba is smarter than me when it's vectorizing stuff for parallel processors, but it is still I think this is this shows that the CPU, because it has low latency access to memory, can pretty quickly allocate an array, whereas the GPU, if you can keep a copy of an array around, like you can keep like just an array in memory, you can make a lot of speed improvements just by avoiding allocations. So we're at the end of the class here, but I just wanted to open things up for questions if anyone had any questions. Yeah. Could you stop the recording?
Oh, yeah.